Hey, before I get started with the video proper, a little bit of housekeeping to get out of the way first. I've been really sick, i.e., cancer levels of sick, actual cancer. Um, the cancer I had made me anemic, so I didn't have enough red blood cells to carry oxygen through my body, which means I was breathing for nothing, or nothing much. Being severely anemic means you can't move around, you can't exercise, you struggle for every breath. The most basic physical activity, especially with a hemoglobin count of 43 like I had, which is really low, um, any physical activity is strenuous to say the least. Standing up, actually, when I was dying, I was a few days from death at the worst of it. Just this, putting a hand up, doing this, was like running a marathon. That's how sick I was. As a result, my muscles atrophied. It's harder for me to catch my breath. I'm doing a lot better now. I mean, the cancer's gone. I'm totally fine there. But physical activity is still not easy for me. It's going to take me a while to get back to my, you know, into a decent shape, I should say. Um, I'm working on it for now, though. Everything's still a bit of a struggle. Doing a lot better than I was, but I still tire out very easily, and that won't go away until my body catches up to all the near death experience I had. That being said, I'm not looking for sympathy or anything. I'm doing fine now. I'm actually doing great. Everything is wonderful. I thought the whole I almost died, and now the colors are brighter, and I thought that was a cliche, but I hate to say it, it's really not. Um, it's weird. It's really weird. So yeah, I tire out more easily. I put on a few 100 pounds. I don't know if how much exactly. I'm exaggerating with 100, but I did put on a lot of weight. And when I got out of hospital and I was recovering from surgery, I ate a little bit too much, perhaps. So I packed on a few more pounds. I'm working on it. All you have to worry about is that I was really sick. It weakened me. I'm still weak, still a little bit sick. So during the video, it might be annoying to have to put up with this kind of thing where I still have trouble breathing and my nose clogs up for no reason all the time. I'm sorry. I don't know what to tell you except that I know it's annoying. I'm dealing with it all the time, not just in a video. I apologize. That being said, I'm going to do my best to get through this as effectively as I can. It's not my first take. Fuck, it's not my first take. I lost count trying to get through it. So, on with the video. Which I have to stop very briefly to mention. One of the things I realized I never made explicitly clear in previous videos, I think I implied it. I'm not an expert. I'm not a scientist. I'm average. I was good in science in high school, and when I was doing my internship in university to become a teacher, I was in a science class that was doing its exam, and I asked the teacher for a copy, and I got 76 after a decade out of high school. Um, that's my highest qualification in terms of science. I was really good in high school, and I remembered a lot even years later. But I don't have a degree in science. I'm a layman. I don't know how to do research. I don't know how to do anything. I am a schmuck, basically. So why make videos addressing creationist science? It's because I am a schmuck. Because I am average. Because I'm not an expert. And if some loser like myself can read these articles and find obvious, glaring fucking flaws by a doctor, I'll mention him later in the article. If I can find flaws made by a doctor with a PhD in geology, what the fuck is wrong with a doctor with a PhD in geology? Talking about geology. If a high school science student can find obvious fucking errors, this is garbage, right? And that's the point of these videos. I'm not an expert. I don't know how to do research. I am average. And yet, an average guy like myself can find obvious mistakes. So how useless is it? That's the point of these types of videos that I make. If you want in-depth research and the study of sources and analysis and metadata and all kinds of other stuff that I'm getting wrong, if you want that, I'm not your guy. I don't know how to do that. What I do know is the basics. And so, here I am making this video. Now, I originally wanted to make this video. I got the mood for recording another series on April 26th of this year, 2017. And that'll come in. It's been over a month now as I'm recording this, but I felt like doing it, and I procrastinated a little bit. But the date will come into focus very shortly. I did read a little bit of this before. I was doing a trial video in my head to see if it would be a good subject for such a video as mine, and it was. So here goes. On the 26th of April 2017, I went to the Answers in Genesis website looking for an article to debunk, and I found Radiometric Dating Back to Basics by Dr. Andrew A. Snelling, apparently a doctor of geology, written on June 17, 2009, last featured in February 2014. I thought, this looks like a likely video. So here goes. Radiometric dating is often used to prove rocks are millions of years old. What a good start, right? First sentence in, and we already have an example of poisoning the well. Oh, it's not actually proven that rocks are millions of years old. It's used to prove. I don't have a dog in this fight. I don't know much about radiometric dating, except that isotopes are unstable elements, which is why they're radioactive. They emit particles. And it's an odd particularity of radioactive isotopes that they have a half-life. Meaning if you have a quantity of the material, like say 10 pounds, over the course of that half-life, you'll get 5 pounds, with all the rest being turned into whatever that element decays into. So that never changes. That's all I know. That's all I remember from what little I know about radiometric dating. I picked up a little bit here and there, but that's it. I know that's accurate, and I know that the most accurate clocks on the planet work on the basis of radioactive decay, like, sorry about that, like cesium clocks and everything. They work on radioisotope decay rates. That's how accurate they are. The most accurate clocks use radioactivity and the decay rates to measure time. That's how accurate they are. I mean, if radiometric dating is used to prove anything, it's probably going to be more accurate than some jackass making rough measurements, eyeballing it. So already, one sentence in, and we have a really bad start for this guy. But it gets worse. Once you understand the basic science, however, you can see how wrong assumptions lead to incorrect dates. I agree with the latter part of that sentence, surely. If you make an incorrect assumption, then yes, your conclusion is going to be wrong. I mean, if I assume that it's not raining and I go outside on the assumption that it's not raining, and it is raining, I'm going to get wet. I can't just say, well, I assume that it's not raining and therefore it isn't. I'm not going to get wet if I go outside. Well, you're going to be wrong, motherfucker. Oh, you thought I was going to make a sarcastic remark about how the wrong assumption in this case was that the Bible is inerrant and completely correct, and therefore their creationist dates are going to be wrong too? You thought I would make that sarcastic comment? You were right. I totally did. First two sentences in, and we're already facing a lot of fucking mistakes. Right there. Let's keep going. Most people think that radioactive dating has proven the Earth is billions of years old. Yes, because it has. In fact, if I remember my watching of Cosmos, the one with Neil deGrasse Tyson, they mention Claire Cameron Patterson, who accidentally discovered the age of the Earth when he was trying to date, I think it was zirconium, and found that lead was contaminating everything, and is the person single-handedly responsible for the death of the leaded gasoline industry. Because that's how science is going to work. Everything is connected somehow, and by trying to date a specific type of rock, you can disprove the safety of leaded gasoline. Sometimes it's weird. But yeah, radioactive dating has proven the Earth is billions of years old, just ask Claire Patterson. After all, textbooks, media, and museums glibly present ages of millions of years as fact. Millions. He just said billions, but whatever, who cares? Millions and billions. If we go back to, what was it, Kent Hovind? Millions and billions. Millions and billions. Glibly, though. Glibly. I mentioned April 26th, because that's the day I selected this article. And I wasn't sure about my definition of the word glibly. You find an unfamiliar word, and from the context, you interpret what that word could possibly mean. It's how your brain creates language. You create your lexicon from context. Nobody says, glibly, this is a word that means this. I wasn't 100% sure that I had the definition of glibly correct. I know potion of glibness in D&D, so I could assume what it does from what the word means from the context of what the potion does. But I wanted to be sure. So I went to dictionary.com and I looked up glibly, and I found the definition was more or less what I thought it was. But the word of the day was very amusing to me. Perfidious. Deliberately faithless, treacherous, deceitful. I thought, how perfect is it that the Answers in Genesis website, in making me look up the definition of a word, shows me the word of the day that perfectly represents Answers in Genesis. Deliberately treacherous and deceitful. Ah, boy. Glibly. No, actually, textbooks, media, and museums do not glibly present much, except if you're talking about news media, which glibly presents science because journalists are not scientists. Textbooks do not glibly present anything. They are not deliberately deceitful. They present the scientific consensus because they're science textbooks, and they have to have some measure of accuracy, or else they're not very good textbooks. That said, the people who select the textbooks can be deceitful, as we saw in the Dover trial. But hey. Oh, and museums don't glibly present anything. They tell you why they think that. And you see this from Creationists a lot. The scientists believe, they hypothesize that. There's this uncertain language in science, and in museums they will say, geologists believe the age of the Earth to be this. So they're being deliberately deceitful by not asserting something as 100% fact. Right, Snelling, you fucking imbecile. They're glibly presenting it as millions of years, as factual, because it's billions of years. You fucking simpleton, Snelling. We're 2 paragraphs in, and I'm already pissed off. Not a great start. Not a great start. Yet, few people know how radiometric dating works or bother to ask what assumptions drive the conclusions. Sure, not a lot of people know how radiometric dating works. Physicists, perhaps chemists, perhaps geologists know how radiometric dating works, Snelling, but then they don't have to. Unless you study the field, you might learn about it or find out from some YouTube video that covers this topic. But yeah, okay, most people might not know how radiometric dating works. It's actually quite simple. It goes back to the half-life thing. 10 pounds of plutonium isotope X, whatever. It has a half-life of 20 years, which means that in 20 years, your 10 pounds of plutonium X will be 5 pounds of plutonium X, and a little bit less than 5 pounds of whatever plutonium X decays into, because they're losing that radioactivity, and that's a tiny little bit of weight, because the weight of an atom has to do with all the weights of the protons and the electrons and the neutrons combined together, and if you lose electrons and protons and neutrons, the atom's weight is lost, and the radioactive particle that flies off has a weight to it, and so it's a little bit less than 5. But that's the basics of radiometric dating. Half-life is the life of half of the substance. How much substance you have left after that amount of time from the original starting thing, you have half. And then if, using my example of 20 years later, you're not down to 0, you're down to a quarter. And then 20 years later, you're down to 1/8. And that's basically an extremely simplified version of radiometric dating. You calculate the leftover radioactive material, and then you calculate, or you measure how much, what's the word? The daughter substance is, the parent and the daughter substance. Like, let's say plutonium X decays into plutonium C. Well, if you have 15 pounds of plutonium C and, I don't know, 4 pounds of plutonium X, or whatever, I'm using up made-up numbers, so the math isn't going to work out, but you can tell how old the particular circumstances of that plutonium X would be, because you have this much leftovers and that much original, and you know the half-life, and therefore you can add them back up together and get to the total age. Like I said, super simplified explanation of how it works. Not a lot of people know that. Fine, that's great. And if I'm a little bit wrong, or if I'm a lot wrong, like I said, I'm just some average guy, I have a high school diploma, that's it. I'm not an expert, I'm just using what little I know for the simple explanation of how radiometric dating works, from what I know. Or bother to ask what assumptions drive the conclusions. Well, the assumption is, if you have plutonium X, like I said, which has a half-life of 20 years. Over 20 years, you can actually measure it. You have another substance. Let's say, how can I best explain this? Uranium W. You might have heard of U-238 if you ever played StarCraft. That's uranium isotope 238. That's the weight of the atom, or the number of, I think it's the number of protons in the atom, which means it's unstable because uranium has a specific number of protons or something like that, or is it neutron? I forget. Either way, uranium W. You have plutonium X, and you can measure the age of the half-life of plutonium X, and then you have uranium W, and you have a quantity of uranium W, and you watch it a little bit, and it decays into strontium N. Great. So uranium W decays into strontium N. I'm completely making things up. And you have a huge amount of strontium N, and you observe the decay of uranium W by a tiny little amount over this period. You can extrapolate, and uranium W has a half-life of 20 million years, based on the amount of strontium N you found and the uranium W. Well, how do you measure that? You confirm it with the plutonium. The plutonium decays at a constant rate. The uranium W decays over the course of your observation at a constant rate. It's not the same rate, but you can observe the decay. And as you observe the decay, you keep making your measurement more and more accurate because you have a larger size of analysis of how much it decays, and then you extrapolate that that's how fast it decays, and you can confirm these things with each other, because if some other thing would mean that it's impossible for the universe to exist, then your measurement would be wrong. But everything fits together. I'm overly simplifying because I don't understand it perfectly myself, but you can cross-confirm your observations in science. This is why tree ring dating comes up. You can confirm the age of some things using tree ring dating, because trees grow at a pretty constant rate on average, and so you count back, and maybe you're a few years off at the end, but you're certainly not billions of years off using tree rings when they make maybe 2 rings a year. You count the number of rings, you get the number of years. If it averages out, great. Creationists often dislike dating methods, especially the cross-confirming properties of various dating methods, because they say things like, well, trees grew faster in the past. How do they know that? You have one assumption, which is that it averages out because trees grow a certain way, and you see them grow a certain way, and that makes sense the way it is. Or you have trees grow a certain way, but some magical circumstance happened to make them grow 16 rings a year for 24 years. And how do you know that? What observation are you bringing to the table to verify that? If tree ring dating is incorrect, then those other assumptions are incorrect, creationists think. Therefore, all of science is wrong. But if one thing about science is wrong, it affects other topics, like, say, computers working. So yeah, in some strange way, if tree ring dating is incorrect, then computers can't work. But creationists don't understand that, so they bother to ask what assumptions drive the conclusions, so they can do what Gleb Beck does. And I'm just asking questions without thinking of what those questions, if you ask them, means for everything else. So yeah, to repeat the question, yet few people know how radiometric dating works, including creationists, or bother to ask what assumptions drive the conclusions, except scientists do. They do, and they understand the assumptions that are made, and the assumptions, if you make them, reality works, and if you don't make them, nothing works. Up is down, left is right. If I sit on a chair, it turns into a duck randomly. So maybe few people know how radiometric dating works or bother to ask what assumptions are the conclusions. That doesn't fucking matter. Your plumber doesn't know either. Does that mean science is wrong? Or does it mean that he knows plumbing? It means he knows plumbing. So let's keep going. Let's take a closer look and see how reliable this dating method really is. Well, the answer is it's pretty fucking reliable, because the world time clock uses radioactive decay, as I mentioned earlier, but whatever. Atoms, basics we observe today. Each chemical element, such as carbon and oxygen, consists of atoms. Correct. Carbon is a type of atom, oxygen is a type of atom, uranium, plutonium, and strontium are types of atoms. What differentiates them is, well, they're going to go into it a little bit, so I'll read the description, because it's not far off. Each atom is thought to be made up of 3 basic parts. Thought to be made up of 3 basic parts. I spoke a little bit too soon there, didn't I? Each atom is made of 3 basic parts, but those basic parts are also made of more basic parts, like quarks and other stuff that I don't fucking know about. But sure, 3 basic parts make up an atom, and those are The nucleus contains protons, tiny particles each with a single positive electric charge, and neutrons, particles without any electric charge. Orbiting around the nucleus are electrons, tiny particles each with a single negative electric charge. So yeah, as the basics, that works. Sure, they're made of quarks and all that stuff, but basic components of an atom: proton, neutron, electron. Sure. The atoms of each element may vary slightly in the numbers of neutrons within their nuclei. So, I remembered wrong, but it is to do with the neutrons, radioactive elements. As far as I know, that's most of the cases, if not all of them. I don't know for sure. These variations are called isotopes of that element. So U-238 has 238 neutrons, if I'm right. While the number of neutrons varies, every atom of any element always has the same number of protons and electrons. I was wrong before, that's why it's just neutrons. So, for example, every carbon atom contains 6 protons and 6 electrons, but the number of neutrons in each nucleus can be 6, 7, or even 8. Therefore, carbon has 3 isotopes, which are specified carbon 12, 13, and 14. I guess, yeah, like I said, I'm not an expert. I read this over a month ago. I didn't remember everything. Forget what I said. Uranium-238 is the weight of the nucleus. Combine the protons with the number of neutrons. Carbon has 6 protons, so carbon-12 has 6 neutrons. That's stable. Carbon-13 has 6 protons and 7 neutrons. According to his little graph here, that's also still stable. And then there's carbon-14, which most people have heard about. Carbon dating is done with C14, which is unstable because it has 8 neutrons, and one of those is going to want to fly off, or 2 of them are going to want to fly off. Radioactive decay. Some isotopes are radioactive, that is, they aren't stable because their nuclei are too large. If I'm going to simplify from a layman's perspective, think of playing with magnets. When you have 2 magnets, they snap together. If you try to twist the magnet, it pushes away a little bit. The nucleus of an atom is kind of magnetic. The positive electric charge, electromagnetism, has a magnetic attraction. If there's too much positive and too many neutral, the number of electrons is going to be the same, but the neutral ones are not going to be able to fit there. I don't know exactly how neutrons stay, but too many of them, they're going to want to leave. And they leave at a constant rate, which is how radiometric dating works. That's the half-life again. To achieve stability, the atom must make adjustments, particularly in its nucleus. In some cases, the isotopes eject particles, primarily neutrons and protons. So I was a little bit right. The protons do sometimes leave. Hey, you can learn even in a Creationist article, you just have to be careful. In some cases, these are moving particles measured by Geiger counters and the like. The end result is a stable atom, but of a different chemical element, not carbon, because the atom now has a different number of protons and electrons. No. That's true for carbon. Carbon-14 might decay into something else. I don't know exactly, but it doesn't always turn into a different element. I know of a few dating methods where the element that is unstable, an unstable isotope, a radioactive isotope, decays into the same element, like argon. I think there's even polonium. I'm not entirely sure. You can look it up on the internet. It's not always a different chemical element. Now, as a simple primer for radioactive decay, I could allow that it's usually the case. There's maybe 3 or 4 radioactive dating methods that have one element turning into another isotope of the same element. It's not common, but it does happen. So as a basic primer, I could leave that go. But it's not a basic primer. It's a disinformation website on a creationist website by a lying sack of shit. So the implication here is suspicious. It's wrong. It's not very wrong. It's just, it makes you wonder why he would assert that it's always a different one. He doesn't use the word always, but he says it is a different chemical element after it decays, when that's not always the case. It makes me suspicious. It makes my hackles rise up. It's, why would you say that if you know it's not true? Is it because Satan? Is it because you're trying to push an agenda on your misinformed idiot sheep? It's suspicious. I could grant it if it wasn't for where I'm finding this information. Continuing, this process of changing one element, designated as the parent isotope, into another element, referred to as the daughter isotope, is called radioactive decay. The parent isotopes that decay are called radioisotopes. Radioactive isotopes, radioisotopes. Sure. Okay, so far so good. Actually, it isn't really a decay process in the normal sense of the word, like the decay of fruit. Yeah, it's not. I don't know why he mentioned that. Maybe the audience of this article is so misinformed that they would assume that that's what happens. Maybe. Sure, okay. The daughter atoms, continuing, are not lesser in quality than the parent atoms from which they were produced. Both are complete atoms in every sense of the word. I'm getting a very no transitional forms vibe from that. Maybe it's just my my pessimism coming into play here. But yeah, this is true. An atom is protons, neutrons, and electrons. There's no such thing as a lower quality atom than another atom. They're all identical. The only difference is between atoms, how many protons, neutrons, and electrons, and that's it. Geologists regularly use 5 parent isotopes to date rocks: uranium-238, uranium-235, potassium-40, rubidium-87, and samarium-147. These parent radioisotopes change into daughter lead-206, lead-207, argon-40, strontium-87, and neodymium-143 isotopes, respectively. Thus, geologists refer to uranium-lead, true versions, potassium-argon, rubidium-strontium, or samarium-neodymium dates for rocks. Yeah, those are how you call dating methods, which is why earlier I said argon-argon, or polonium-polonium, if I'm remembering that one right. You refer to the dating method using the 2 parent and daughter isotopes, including when it's the same thing. It's, again, suspicious to me that he mentions a bunch of them without referring to any of the same ones. I'm pretty sure argon-argon is used to date rocks as well. I could look it up, but you can pause the video and do it. It's going to be boring if I do it. So look it up. There's a lot of dating methods. There's not just 5. There's a lot more than that. Maybe they regularly use those 5, but combined with the fact that he didn't mention that in some cases there's the same parent and daughter element with different isotopes, and then referring to 5 that don't have the same thing, it makes me question why he's not referring to them. Or why use just the 5 regularly used ones when he could easily address all of them? I don't know why he's doing it. He's supposed to be a doctor in geology. Why? Why is he not mentioning them? Now, redeeming quality, continuing, note that the carbon-14 or radiocarbon method is not used to date rocks because most rocks do not contain carbon. Yes. In the words of, was it Potholer 54? There's no fucking carbon in it. If you're analyzing the bones of dinosaurs, which are millions of years old, there's no fucking carbon in them. They've been fossilized, which means all the organic matter was replaced by minerals. And I'm sorry for doing this, but I have to. I really have to learn how to edit videos at some point to avoid doing stuff like that. I'm sorry. So yeah, 1 point in Snelling's favor. He's made a few good points so far. It's a refreshing change from Canthoven, who doesn't get anything right. Yeah, carbon-14 is not used for rocks because rocks do not contain carbon-14. Carbon-14 is something ingested by living organisms, and barring the reservoir effects or mollusks, it's used for organic fossils of organic or animals or plants or stuff like that because, well, it's something done by plants, and animals eat plants and they accumulate a number of carbon-14 in their lifetime. Then you can date them based on the amount of daughter isotope of carbon-14. It's a point in his favor. Chemical analysis of rocks today. Geologists can't use just any old rock for dating. They must find rocks that have the isotopes listed above, even if these isotopes are present only in minute amounts. Right. At the risk of, I think I stopped reading my original trial pseudo video above that point. So I'm going into unknown territory from this point on, but yeah, if you have a rock with no radioisotopes in it, like what was he said earlier above, lead-207. Right, let's say I'm not sure if lead-207 is stable, but let's say you find a rock with no lead-207 in it. You can't date it. There's no lead-207. There's no uranium-235, I think that would be. You don't know what you're getting into with that one, because you don't have any parent isotope and you don't have any daughter isotope. You can't date it. If you have nothing but lead-207, big old chunk of lead-207, no uranium anywhere in sight, you can't date that either, because you don't know when the last bit of uranium decayed. All you know is there's this much lead, assuming none of it was shaved off. It was this much uranium originally, but you don't know when that was. However, using the daughter isotope, let's say 5 pounds of lead-207, I'm using 5 pounds a lot, you have 5 pounds of lead-207, you know the half-life of uranium-235, using my example from earlier. You can estimate that since uranium decays into that much lead, it took this long. So you have at least a minimum amount of age to the universe using that. You can't date it precisely because it might have been that lead-207 for 15 billion years, but at least you know that it's, I don't know, I'm not going to look up and do the math, but you know that if it takes 5 million years for 5 pounds, or 5 and a bit pounds of uranium-235 to decay into 5 pounds of lead-207, you know that it took at least 5 million years for that to happen. Or the lead-207 formed that way, not radioactively, it just happened in the solar furnaces, which heavier elements are produced, so you don't really know. You know you have at least that minimum, maybe. So, yeah, if there's no parent isotope, you can't date it. If there's no daughter isotope, you can't date it. But if you have daughter and parent isotopes in the same substance, you're ready to date your rock. Most often, this is a rock body or unit that has formed from the cooling of molten rock material called magma. I had to. Examples are granite, formed by cooling under the ground, and basalts, formed by cooling of lava at the Earth's surface. The next step is to measure the amount of the parent and daughter isotopes in a sample of the rock unit. Specially equipped laboratories can do this with accuracy and precision. Again, I'm starting to get suspicious. I didn't mention it, but the examples granite and the basalts, is that the only two examples? I wouldn't question it if it wasn't for the fact that he's gotten some things suspiciously wrong before, and now he's asserting there's only two. And now he's talking about specially equipped laboratories can do this with accuracy and precision. I wonder if by specially equipped laboratories he means laboratories in creation research institutes that have a Bible open at page 12 or whatever. I wonder if that's the special equipment he is referring to. So in general, few people quarrel with the resulting chemical analyses, except creationists. It is the interpretation of these chemical analyses that raises potential problems. Here we go. To understand how geologists read the age of a rock from these chemical analyses, let's use the analogy of an hourglass clock, figure 2. There's a graph explaining a little bit of what I just did about a rock with daughter and parent isotopes. You can measure that, and if you have a solid chunk of uranium-235, for instance, it decays into lead, but you know how long that thing with just the parent isotope is going to take to turn completely into lead. You know the half-life, etc. I explained a little bit of that, and he's making an analogy with an hourglass where you have the parent isotope on top, and as it, grain by grain falls into the bottom of the hourglass, it turns into lead. So you know from how much uranium there's on top and how much lead there's at the bottom, how long ago the hourglass was, activated, how it was turned around and the uranium started to turn into lead. You can measure that. That's the assumption. He goes on to explain it underneath the graph. In an hourglass, grains of fine sand fall at a steady rate from the top bowl to the bottom. After 1 hour, all the sand has fallen to the bottom bowl. So after only half an hour, half the sand should be in the top bowl, and the other half should be in the bottom bowl. Close enough. As I said, if lead loses protons and neutrons and electrons, which it does, it's not going to be quite half the weight, because you have to use moles to measure the weight of a sum of atoms, and it's not like always a straight reduction depending on the amounts of atoms. One atom of a molecule weighs a certain amount, and if you have a certain amount of weight, you can measure the amount of molecules using a mol, M-O-L. I used to be really good in high school at calculating that shit. I forgot almost all of it, but half close enough. What you have to remember is that, sure, if there's an amount of grains of uranium, there's going to be an amount of grains of lead underneath, but the decay pushes out particles, and those particles have weight to it. So it's not quite half, but I'll give it to him. I'll give him close enough for government work. Suppose that a person did not observe when the hourglass was turned over. Oh, here we go. Historical science. He walks into the room when half the sand is in the top bowl and half the sand is in the bottom bowl. Most people would assume that the clock started half an hour earlier, because we can measure the half-life and it's constant, and if the half-life of radioactive isotopes is not constant, then everything you know is wrong. I mean, a lot of science, a lot of technology today relies on the reliability of radioactive stuff decaying at precise rates. You kind of set fire to your house because you question the drapes if you start asking these kinds of questions. It's not, how dare you question science? It's literally, this is how technology works. That's a part of it. If you question that part, you're saying the technology doesn't work the way we think it does, and yet I'm using a computer and a camera to talk to you right now. You're kind of arguing against the obvious by doing this kind of thing. By way of analogy, the sand grains in the top bowl represent atoms of the parent radioisotope, uranium-238, potassium-40, etc. Figure 2. The falling sand represents radioactive decay, and the sand at the bottom represents the daughter isotope, lead-206, argon-40, etc. When a geologist tests a rock sample, he assumes all the daughter atoms were produced by the decay of the parent since the rock formed. Yeah. Unless you want to argue that a substantial part of a daughter isotope wasn't created by radioactive decay and just coincidentally clung to a bunch of parent isotope in the random process of a solar forge fusing lighter elements into heavier ones. Sure, okay, let's just argue that lead-206 just happens to have formed right next to uranium-238. Let's go with that. So if he knows the rate at which the parent decays, he can calculate how long it took for the daughter, measured in the rock today, to form. But what if the assumptions are wrong? What if your mother's a whore? I'm not saying she's a whore. I'm just asking, what if she's a whore? This is the kind of, I'm not sure if it's exactly question begging, but it's the kind of thing Glenn Beck did. Is Obama a communist? I'm not saying he's a communist. I'm just asking the question and then telling you how your life will end if Obama's a communist, because he's a communist and he wants to take your guns. For example, what if radioactive material was added to the top bowl, or if the decay rate has changed? How do you know it's changed? How do you explain that it changed in the past, but when it's measured today, it doesn't change? And the person I live with now just came back in, so there might be noise in the background. How do you know it changed in the past? Well, you assume it does. Let's pretend we live on a floating ball of rock in space, circling around a giant incandescent ball of gas. Let's just call it the sun for the hell of it. Let's assume that. And let's assume that our planet orbits at a varying distance in a egg-shaped orbit, and it's also inclined according to the plane of the ecliptic, at say 23 degrees roughly, and it also revolves around itself. I don't know which direction. I think it's like this. And it goes around the sun, and it revolves. And so if you do the math, you can tell that tomorrow, at this position on the planet, the sun will rise at that time, at that hour, at that minute, at that second. And you do it, and it works. Well, how do you know that tomorrow you'll get an accurate result using the same math? You wait until tomorrow, and you do it, and you get the right result. But how do you know tomorrow you'll get the same result? You do the math again, and you do it, and you get the right result. Okay, how about 10,000 years ago, the Earth went around the sun 10 times as fast? Why would you think that? What magical event happened that made radioactive decay faster or slow down? Or why is he asking this question? What evidence does he have to even suggest that the decay rates must have changed? That's the point. He's asking a question because he doesn't like reality, and he has a conclusion. The Bible is true in everything, even though it's not. It contradicts itself, for fuck's sake. So he has to ask this question, like, what if the radioactive decay rates were faster, or slower, or 12ther? That's not even a word, but what if it is? what if? Well, what if you're an idiot? I hate to be so blunt, but asking the question isn't proof against the theory. You have no reason to assume the decay rate has changed. If you assume the decay rate has changed, everything falls apart. You observe the decay rates and they're constant. Assuming that they're different in the past, you have a problem. But that's the end of part 1. I'm going to scroll back up and do part 2 when I get another chance. So, see you then.